All right, guys, today we're going to be talking about moment of inertia for an object as it rotates. All right, so in just a second, I'm going to roll two balls down a slope. All right, one of them is going to be solid and the other is going to be hollow. And they're both going to start at rest from the top of the slope. I want you to think about which ball is going to reach the bottom of the incline first, how mass and the related force of gravity affects the balls and their acceleration, and what friction does in terms of affecting the balls as they roll down the slope. So I got two sports balls. All right. So tennis ball is in your left, and then I've got this rubber bouncy ball is on your right. All right. So the difference between the two of them is that the tennis ball is hollow. So if you squish it on the inside, there's nothing. So if you just squish it, there's nothing on the inside. Whereas this bouncy ball right here is solid. So I can squish it a little bit, but it's made of stuff. There's rubber throughout the whole thing. All right. So what we want to think about is if I let these two balls go down this incline at the same time, what's going to happen? Who's going to reach the bottom first? Right? Because what we know about things going down an incline so far is that if we allow two things to slide down an incline, if there's no friction, they should get down to the bottom at the same rate, right? Because their parallel component of gravity is going to be proportional to their mass, and their net force is also proportional to their mass, right? So the masses cancel out, we end up with the same rate of acceleration. The same thing happens if we add friction in. However, these two balls are not sliding, they're rolling down the incline. So let's take a look at what happens as we allow them to go. So again, tennis ball's on your left, rubber bouncy ball that's solid is on your right. All right, we let them to go. It's only a small incline, so we don't see them beat each other by too much. But the rubber bouncy ball that is solid beats out the hollow tennis ball, and we're going to explore why that is in this lesson. All right, so as we discussed with the two balls, it turns out that their force of gravity and the force of friction acting on those balls, if they were sliding, would not cause them to accelerate at different rates. However, when they are rolling, we find that they do accelerate at different rates. So, what is the reason that they're accelerating differently? Okay, so let's quickly remind ourselves of torque and angular acceleration. Remember that just like linear or translational acceleration, angular acceleration is going to be produced by force acting on the object that's undergoing the rotational motion. And torque is the rotational equivalent of force, and we can find it with this equation that tau, or the torque, equals radius, or the distance from that axis of rotation that our force is being applied, times the magnitude of that force, times the sine of the angle between those two vectors, the distance and the force vectors. Right? So if we have an r vector right here, and our force is acting like that, then our angle looks like it is a 90-degree angle right there. And as long as the force is directed tangential to the object's rotation, or how we usually direct a force, right? So right here, the hand is pulling that tire tangential to the tire's curve, right? And so that's going to produce a 90-degree angle. So our theta will be 90 degrees. And as long as that's the case, then our sine of theta will be 1. And so that means that we can get rid of our sine of theta because this will just equal 1. So if we are to simplify things as we build up equations here, taking our torque and applying it 90 degrees relative to that radius or that distance from the axis of rotation, then our torque will be equal to our radius times the magnitude of the force. We have already discussed Newton's second law with regard to translational motion. And just to remind ourselves, our net force equals the mass of the object times its acceleration, right? Or put a different way, our acceleration is proportional to the net force acting on that object, but inversely proportional to the mass of that object or that system. And just as a quick reminder, remember that force is the ability to cause change to the state of motion of an object or a system. Mass is proportional to an object's inertia, which is an object's or system's resistance to changes to a state of motion. And acceleration is the rate of change of an object or system's velocity over time, which is basically just its change in its state of translational motion. So let's think about how torque and Newton's second law relate to one another. And just as a reminder, we're going to keep these two equations in our back pocket, that torque equals our radius times force, and that our translational acceleration equals our angular acceleration times the radius. So we can repurpose the equation for Newton's second law and apply it to rotational dynamics. Because again, we've got net force equals mass times acceleration. And knowing that our acceleration, our translational acceleration, equals our angular acceleration times the radius, we can plug that in for our translational acceleration. And we can multiply each side by r, right? So if we multiply by r on the left side, we have to do that on the right side. And on the right side, there was already one r. And so now we end up with r squared. And finally, we know that our radius times our net force is our torque or our net torque. And this now we find is equal to mr squared times our angular acceleration. So let's think about how this equation we just made, the net torque equals mr squared times angular acceleration, fits into that Newton's second law equation, right? That net force equals mass times acceleration. And if we look at this, we know there are analogous components between translational and rotational motion. We know that our net force, the analog for that for rotational motion, is our net torque. And of course, our translational acceleration, the analog for that in rotational motion, is our angular acceleration. So that means that our mass or our inertia, our translational inertia from Newton's second law, is equivalent to this term right here, mass times r squared. And we're going to explore that today because this is what we call our moment of inertia. And again, yeah, that analog between mass and inertia and translational motion and rotation is mr squared. So let's break down our rotational form of Newton's second law. We've got net force equals mass times acceleration, and we're going to compare that to net torque equals mr squared times angular acceleration. We know from Newton's second law, translationally, that our force is the ability to cause change to the state of motion. Mass is the resistant of an object or system changes to a state of motion, and acceleration is that change in the state of motion, right? So let's think about how those things translate over here. And first, we've got our net torque. So our net force is analogous to our net torque, right? So torque is the ability to cause change to the rotational state of motion of an object or system, much like force was the ability to cause change to an object's translational state of motion. We also have angular acceleration. So those two things are equivalent to one another. And whereas translational acceleration was an object's change in its state of translational motion, our angular acceleration is an object's change to its rotational state of motion. And finally, that leaves us with this last term here, where mass was our inertia in Newton's second law. So when we think about translationally, our term for rotational inertia is mr squared. So let's think about this rotational inertia, or what we also call moment of inertia for rotating systems. Moment of inertia, or rotational inertia, is represented by a capital I, and it is an object's resistance to changes to its state of a rotational motion. And we can find this moment of inertia for any point mass with the following formula, that the rotational inertia, or I, at that point is the mass of that point times the radius of that point from the axis of rotation squared. However, objects are made of an infinite number of points, which means that an object's moment of inertia is determined by the sum of all of those moments of inertia of all the points within that object. So this we can use to find a point, but in object, we have to take the sum of all those points. So in math, we would represent this sum as the moment of inertia, or I, to be the sum of all those individual points of inertias, right? Or the sum of each point mass times the radius of that mass from the axis of rotation squared. And so this means that every shape is going to have a specific equation for its moment of inertia. And if the shape is a known shape and it has a uniform mass distribution or uniform density, meaning all the points within it have the same mass, that means that we're going to have a known equation for that moment of inertia for that specific shape. And we can find that known equation using calculus. We can integrate its mass over its radius. However, we aren't going to do that calculus in this class. Instead, we're going to, because each of these specific shapes has known equations, we're going to use those equations as they are. Let's take a look at some of those shapes, shall we? So we've got a few different shapes here, and these are all variations on a disk, right? So if you think about a disk is going to have some height to it. It's going to be a cylinder, essentially, and either its length can be larger or smaller, and its radius can be larger or smaller. So we start out with a solid cylinder. We end up with this moment of inertia right here, I equals mr squared. This is different than if we took and we hollowed out that cylinder. Because if we hollowed it out, we get something like a hoop right here, which has nothing in the interior, and its moment of inertia is just mr squared. However, we start filling that in. So if we go halfway between a hollow hoop and a solid cylinder, then we get something else like this, an annular cylinder, which has an inner wall and an outer wall. And it has a distance between the inner wall and that center of R1, and a distance between the center and that outer wall of R2. And so we can find its moment of inertia with this equation. And finally, one last thing to think about with our disks or our cylinders here is, what about if instead of rotating through that center, along that center of the circle that makes up the cylinder, what if we rotated it at the center of its length? And if we do that, if we rotate it around in that direction, we end up with a very different moment of inertia, because now we're rotating it around a different axis. And so what's key to note here is that our axis of rotation matters, right? So if we take a solid cylinder, both of our bottom ones are solid cylinders, but if we rotate around a different axis, if we rotate around the center of that circle, we end up with a moment of inertia of 1/2 mr squared. But if we rotate around that the center of its length, the middle of its length, we get a moment of inertia that equals mr squared over 4 plus mass times the length squared divided by 12. So let's compare between two different shapes, right? So we've got a cylinder or a disc will look like this, right? And if it is solid, it has its moment of inertia equals mr squared. However, we can take a sphere, and a sphere isn't going to be as symmetrical along its length as a cylinder is, right? A sphere is going to be curved, and so it's going to have a different moment of inertia. So if you have a solid sphere, its moment of inertia is going to be 2/5 mr squared, right? And just like taking and hollowing out that disk will give you actually a greater moment of inertia, because now more of that mass is concentrated further away from that center, the same thing will happen with a sphere. If we take and now, rather than having this whole sphere be filled in with solid, a dense distribution of mass, now we have an empty space in between the center of the sphere and the outside of the sphere. And our moment of inertia similarly increases when we take that mass and distribute it to the outside. So the further a mass is from that center, the further we go, the larger our moment of inertia will be, right? And we see this again comparing a hoop versus a solid cylinder, that as we increase our, as we take that mass and hollow at the outside and distribute that mass further and further to the outside till we get to a hoop, we end up with a larger moment of inertia for the hoop. And the same thing happens with the sphere, right? If we take our solid sphere, where we've got a uniform distribution of mass from the outside to the inside of that whole sphere, and it's all filled in. And then if we take and we hollow that out so that the sphere only has its mass around the outside, a hollow sphere is going to have a larger moment of inertia than a solid sphere would, because that mass is now further away from that axis of rotation. And then again, if we go back to our rod or our disc, we can think about rotating it around different axes. So if we take our cylinder and we rotate around that central axis, we end up with one one moment of inertia, right? But if we take and we rotate it around the center of its length, so around there, then we end up with a different moment of inertia, right? And if that cylinder were actually infinitely small and the rod were so thin that we didn't have to worry about that radius of the disc, we could just end up with ml squared. If this radius is small enough that our radius almost equals zero, then this term from our solid cylinder goes away. So then if we take and we move that axis of rotation from the center of its length to the outside of its length, we end up with a big swooping circle that it makes as it rotates around that axis, and that will give us a different moment of inertia as well. And now this will take our mass times L, which is our new radius, right? Really, L is our distance away from the axis of rotation. And so if we take mass times L squared over 3, that gives us our moment of inertia there. So we've got a bunch of different moments of inertia for different shapes, and we're going to play around with these as we go through different problems. Okay, so let's find the moment of inertia for an object. And let's take, for example, the solid ball that we released at the top of the incline at the beginning of this lesson. And if we rotate around its center, so if we're rotating around its center like this, then we will have a moment of inertia for a solid sphere of our moment of inertia equals 2/5 m times r squared. All right. So for an object, for a solid sphere, if we know our mass equals 1.25 kilograms and our radius equals 8 centimeters, 8.00 centimeters, let's get these into our base units, which means kilograms. We're good to go. But 8 centimeters, we want to convert that into meters, and that's 0.0800 meters, right? So let's find our moment of inertia here. We'll take 2/5 times our mass is 1.25 kilograms times our radius is 0.08 meters squared. And this should give us a number that is 0.008. And let's think about our units here. Our units for moment of inertia should be, we've got kilograms times meters squared. So this is in kilograms meters squared. So moment of inertia will be in kilogram meters squared. Are our units for moment of inertia. And this is how we find the moment of inertia for an object. First, we got to figure out, well, where are we rotating it, right? And in this case, we're rotating around the center. And from that, as long again as is a known shape with a uniform distribution of mass, then we have an equation to use for its moment of inertia. And from that, if we know its values, its mass, and its radius, we can find its moment of inertia. However, there's one other specific thing that we're going to think about, which is, what if we take an object and we revolve it around an axis of rotation? So rather than just rotating it around an axis that's inside of itself, if we take and we revolve it around an axis. So for instance, we've got this hockey puck over here, and this hockey puck is being revolved around an axis of rotation, right? So our axis of rotation is right here at the center. So we're moving that mass around that axis of rotation, which means that if we take our take our sum of our mass times our radius squared, we end up with this equation, because we actually could treat our entire mass as a single point that is centered exactly at its center of mass. So if we just take the location of that center of mass is the radius, right, and we square that times the mass of our entire object, we end up with our moment of inertia equals mr squared. All right, so let's take a moment to think about what equations you're provided with on the AP reference sheet, for which I made a handy little infographic meme here. The meme shows Drake, and he's saying no to a couple of things. He says no to this equation right here, which is how we originally talked about torque, right? Their net torque, use mr squared times alpha, or angular acceleration. And that is not something that you are given on our table of information. However, we are given this, which instead of using mr squared, replaces mr squared with I, right? And then obviously reorients our equation so that we solve for our angular acceleration of our system. This is our angular acceleration equals the sum of our torques or our net torque divided by the moment of inertia of our system. Likewise, you're not given this equation right here. You are not given that our moment of inertia equals mr squared. What you are given is this guy right here, that our moment of inertia equals the sum of all of the points of within our object, right? Or the sum of mr squared for all of those points, right? However, it is left to you to figure out what your shape is and how your actual equation is going to look from this equation right here. So for this equation right here on our AP table of information, or sorry, on our AP exam, you'll be given the moment of inertia for each specific shape within the question. In this class, I'm going to give you a table, a reference table for all the different shapes that we just talked about and then some, so that you can select based on the shape within your question what the moment of inertia for that shape should be. However, you do need to know that for a center of mass that is revolving around an axis, you can use this equation right here, right? That we can treat that whole object as its center of mass, and we can use the entire mass for the center of mass, and we can find its moment of inertia using this equation, right? So you do need to know which equation to employ for a given problem. So let's put this into practice with this example problem. We have a dad or a big brother pushing a merry-go-round, and that merry-go-round weighs 50 grams. So I'm going to put over here the mass of the merry-go-round equals 50 kilograms, and the father is exerting a force of 250 newtons. Right? And finally, he's exerting it at a radius of 1.50 meters. And so our first question is, what is the angular acceleration when no one is on the merry-go-round? So when no one is on the merry-go-round, we have this equation right here that gives us our angular acceleration equals our net torque divided by our moment of inertia, right? And so in this case, we want to find what our angular acceleration is. We don't know what that is. And we need to know what our torque is and what our moment of inertia is, which we aren't given right off the bat, but we do know that our torque equals our radius times the force, so the radius where that force is applied times the force times sine of the angle between those two things. And since we're told right here in our problem that we have a 90-degree angle, we know that our radius of 90 degrees is just going to be 1. So we're really just looking for a radius of where that force is applied, which is 1.50 meters, times the force, and the magnitude of that force is 250 newtons. And so if we take 1.5 times 250, we'll end up 375 Newton meters is our torque that the father's applying to that merry-go-round. And if our merry-go-round is just a solid disc, so this is a solid disc, then we want to find from our reference or from the problem that we're given our moment of inertia for that solid disc. And we can find that our moment of inertia for a solid disc is 1/2 times mr squared. So m being the mass of that object, r being the radius of that object's shape, and then the square of that. So we could take 1/2 mr squared is our moment of inertia for this object. So that would be 1/2 times the mass of the merry-go-round, which is 50 kilograms, times its radius, which again is 1.5 meters, and squared. If we do have the math on that, we should get 56.25. And this is kilograms meters squared would be the units that we end up with, right? Kilograms and meters squared. Okay, great. So I accidentally deleted everything. But if we want to find our angular acceleration should equal our net torque, which since our father is the only thing applying a force on here, he should be the entire net torque divided by our moment of inertia. So let's plug that in over here. Our net torque divided by our moment of inertia should give us our angular acceleration. So we're looking for 375 Newton meters divided by 56.25 kilogram meters squared. And we end up with a number that is 6.6666 repeating. So we'll call that 6.67. But let's think about what units we have here, because remember, we've got Newton meters on top and we got kilograms meters squared on the bottom. But if we pull those out, so Newtons, right, is kilograms meters per second squared, right? Is there newtons? And that is times meters and then divided by kilograms meters squared. So ultimately, what we have here is kilogram meters times another meters on the bottom, right? And so one of those meters cancel out, another meter cancel out, kilograms cancel out. We end up with, in this case, just 1/second squared. Or if you wanted to, we could call this radians per second squared, which is exactly what we would expect angular acceleration to be in, right? So our angular acceleration here equals 6.67 radians per second squared, or just 6.67 inverse seconds squared. All right, so now let's take and we're going to add on a child, okay? And the child is going to sit at a radius, so the radius of the child equals 1.25 meters away. And her mass is 18 kilograms. So if we want to find our angular acceleration at this point, we're going to take our angular acceleration and we're going to take our torque and divide that by our moments of inertia. However, in this case, we have a moment of inertia for both the merry-go-round and for the child. So we've got to figure out both those things, right? Because our moment of inertia for this whole system is comprised of both the merry-go-round and the child itself. So we have to take both into account. So let's think about what we've got here. So we know from what we calculated before that our torque from the father is 575 Newton meters. And we knew that our moment of inertia for the merry-go-round was 56.25 kilogram meters squared. So we've got to figure out what our moment of inertia for the child is, right? And if we think about it, the moment of inertia, the child has a center of mass, and that center of mass is revolving around an axis of rotation that is outside of her mass. So that means we can treat her as just a point in space, and that we can use our basic equation for moment of inertia here, because her moment of inertia is her mass times the radius, her radius squared. So we can take her mass times her radius and square it, and we end up with her moment of inertia. So her mass is 18 kilograms. Her distance from the axis of rotation that she is circling is 1.25 meters, and we're going to square that. And that should give us a moment of inertia of 28.125 kilogram meters squared. So for our angular acceleration, we have the same torque as last time, 375 Newton meters is what the father's applying to the merry-go-round, whether she's on it or not. However, now we have both the merry-go-round's mass and moment of inertia that he has to accelerate, which is 56.25 kilogram meters squared. And we have her mass and her moment of inertia that he also has to accelerate. So obviously, if he applies the same torque to this system, now with her added on, it's probably going to experience a slower rate of acceleration. All right, if we plug all that into the calculator, we'll end up with our angular acceleration. And our angular acceleration now is 4.44. And again, our units should be radians per second squared because our kilograms and meters will all cancel out. So you'll notice again that our angular acceleration is less now than when we originally when the guy was originally accelerating just the merry-go-round by itself, right? And that's not surprising because if you put something on top of something else and you use the same force or the same torque to move it, you'd expect you'll end up with less acceleration because now you have to accelerate more mass if you're moving a translationally, or in this case, more inertia, more rotational inertia you have to move as you're rotating around here. All right, great. So now we've got a problem set for tonight. Please use this idea of moment of inertia to figure out how that relates to angular acceleration and how we can calculate moment of inertia for different objects as we take a look at these problems. Thank you.